This video looks at solving simultaneous linear equations with matrices. Now, if we have a system of equations, ax plus by equals k and cx plus dy equals m, we can turn these into matrices. So in our first row, we have our first equation. So our coefficients of x and y are a and b. And then our solution goes on the other side. Then our second equation, our coefficients are in the second row, and the solution m is on the other side. Now, this is exactly the same as saying a matrix A times by x, matrix X, equals B. So A is A, B, C, D, X is X, Y, B is K, M. And now we can solve them using our previous methods with inverses. So if we have AX equals B, to get the x on its own, we would pre-multiply by the inverse of a. So that means we have to pre-multiply on the right-hand side. Now this is assuming an inverse for a exists. Remember, there may not be a solution for simultaneous equations. What if you had parallel lines? Those lines never meet. There is no point of intersection. So just remember that. So that means our inverse a times by a is I, so we're left with x on the left-hand side, so that's the inverse of a times b. So again, you have to pre-multiply. Order matters. Now, simultaneous equations without a unique solution, if you have two parallel lines, as I've just mentioned, then a non-invertible matrix results. You can't have an inverse. So x plus 2y equals 3, negative 2x minus 4y equals 6. If I rearranged our two equations, this would give 2y is 3 minus x, y is 3 over 2 minus x over 2. This one would give 4y equals minus 2x minus 6, y equals minus x over 2 minus 3 over 2. So you can see here, my gradient is negative a half, and in this one, my gradient is negative a half. These are parallel lines. So you won't have a solution. But just showing that, if I wanted to work out the determinant, once I've come up with my equation, I end up with a determinant equaling 0. So if our determinant of A equals 0, remember there is no solution. So let's look at some examples. Solve the following equations. So set up your matrices. So you have 3, negative 1, 2, 3, x, y equals 7, 1. Now we're going to do these using the calculator because in all honesty, it'd be quicker to solve them by hand, probably, just using simultaneous equations. So let's do them by our calculator, but let's set it up first. So this will leave x, y equals 3, negative 1, 2, 3 to the negative 1 times 7, 1. And go to your calculator. So working that on our calculator, we have our 2 by 2 matrix. 3, negative 1, 2, 3. I want the inverse of that. So the negative 1. And I could do the intermediate step and write what the inverse is, but I'm just going to go straight to timesing that by the 2 by 1. Which is 7, 1. And there's my answer. So x equals 2, y equals negative 1. So our answer is 2, negative 1. Now remember, you can check your answers. Go back to your original equations. X is 2, 3 times 2 is 6. 6 minus negative 1 is 6 plus 1 is 7. So that works. Look in your next one. 2 times 2 is 4. 4 plus 3 times negative 1 is negative 3. 4 minus 3 is 1. So remember, you can check your solutions. Let's look at the next one. So coefficients 3, -1, 2, 5. Be careful. They might have tried to trick you up and they're not in the order of x then y. So remember, it's always x then y when you're doing your coefficients. 16 and 5. So that would mean my xy would be the inverse 3, -1, 2, 5 to the -1 of 16 and 5. Always do a quick check that you do have a determinant. So 15 plus 2 is 17. So the determinant exists. So therefore your inverse will exist. It just saves you going to your calculator and putting it all in just to find out there is no inverse. So looking at the next one, I have a 2 by 2. So which is 3, -1, 2, 5. I want the inverse of that, so to put it to the power of -1, and then I want to multiply it by my 2 by 1. Which is 16 and 5. And I get 5, -1. And your answer is 5, -1. Again, check, go back to your original. 3 times 5 is 15. 15 plus 1 is 16, so that works. 2 times 5 is 10. 10 minus 5 is 5, so I know that's correct.